Okay. Yeah, I will just wait until 10:05, and I think there's two more people to come, but yeah. Okay. Yeah, another Friday. Hmm. How's everyone doing? All right, so it's 10:05. We should get started. Okay. Yeah, as usual, briefly review about yesterday. Yesterday we talked about selection sort and insertion sort, right? And those are two of those basic sorting algorithms that is pretty um, beginner friendly, I would say. Yeah, selection sort is just the idea of finding the minimum every time, and then sort it, right? And then insertion sort. Insertion sort is just that you need to, when you try to play cards, it is similar. So you sort of just take one element and then try to sort it and take another element and, and then append that into the sorted list and try to check where should it be placed, right? And then this is the flow chart, for the selection sort. Yeah, so read the length of array in N and the array in array, and then set I is equal to 0 as I is less if I is less than N minus 1. Then we're sort of setting up a minimum index, and then we try to loop through the rest of the array, see if that is minimum. If that is minimum, then update the array, and then after you're done with checking if that is minimum, you try to swap it with the i's position, right? And then I will just move on, right? I will just be plus plus. Plus plus means I plus one, right? So you should just check this condition again and go on forward, and then just at the end print the sorted array, right? And then the code seems to be fairly simple. You have an array. Yeah, you just for loop have an I, and then you have another for loop to check after I, and then whatever is after I, you select the minimum, and then swap with the position I. Okay. Yeah, so the best case, average case, worst case will just be n square. You have to check, everything like sort of in a square fashion anyway, twice. So yeah, in a double for loop. So that is why it is n square. So yeah, it doesn't get any better if it is already sorted, because the same operation will be like that anyway, right? Okay. So let's continue with the insertion sort. Insertion sort is a simple sorting algorithm that works familiar to the way that you play cards, right? And then the array is virtually split into sorted and the unsorted part. And then the values from unsorted part are picked and placed in the correct position in the sorting part, right? I think explanation explain it really really well. It is what this sorting algorithm is, and then the algorithm is just for example, to sort an array of size n in the ascending order. You iterate through array 1 to array n over the array, and then compare the current element to its predecessor, which is the one in the front, one element that is before it, right? And then if the key element is smaller than its predecessor, then compare it to the elements before, right? You just keep comparing, and then until you make until you find the correct place to put, right? Okay. So yeah, here's an example. You have I as equal to 1, and then second element of the array, and then 2 to 4, which is the last element of the array 6, right? And then 11 and 12, 11 is less than 12, then swap, right? And then we take 13, we check it is in the right position already. We check 5, and then you just swap all the way to the front. And then you take 6, and then you put it into position 1, right? And then yeah, here's the source code. So again, a for loop ranging from 1 to the length of array, and then a key, that is equal to array of I, right? That way, you will know that what is the position that you're trying to insert, right? What is the unsorted list value that you have, right? And then you're trying to compare um, the numbers in the front, right? J is equal to minus 1, right? And you will have to um, fit the condition of J is larger or equal than 0, and then key is less than array of J, right? And then if that is the case, then you swap it and decrement J again. And then after the for loop, we just make J plus 1 is equal to key, because right now J is pointing to the number that are less than the key, right? So that is why you need 2 plus 1, so that it is actually inserted into the correct order. Okay, and yeah, the rest is just the driver code, so it doesn't actually mean a lot. Okay, and the best case scenario is when the element is already sorted, right? So when the element is already sorted, then this while loop, doesn't even get into it, has a chance to get into, because the key will always larger or equal to array of J, right? So you can only treat it as a ON algorithm, where you, like, no matter how many elements is, you just loop that much times, then it'll be good. Okay, and but other than that case, right? Like other than that particular sorted case, then all other cases will actually need to get into the while loop, and just iterate through it, so that it gets sorted, right? So it is on average, or the worst case is still n squared. Okay. Yeah. Okay. So I finished review this. Also, yesterday we talked about the idea of stack and queue, right? And then stack and queue is just the, I would say, the data structure that is I don't know, maybe easiest. I don't think it's easiest, but it is definitely most useful data structure um, when you started programming, right? And then in Python, thanks to the list, the built-in function of the lists, you can actually implement stack and queue just using lists instead of using other kind of other kind of library or the classes that you write yourself. Okay, and in terms of queue, it is first in, first out, right? Imagine you are standing in front of a cashier, or you're waiting for to order in a restaurant. Then you're in a queue, right? It is sort of like first come, first serve, principle, and then just first in, first out, right? And then you can have this you can have this function called pop, and then if you pass in the parameter 0, then it will pop from the front, right? um, as you can see, the first element that you append is 1, and then the first time you call pop, 1 is no longer there, right? And then you do it again, then you just pop in the front, right? And stacks and queues are just brothers and sisters. They just always sort of come together. All right, and then a stack. You can think of a stack of bugs, right? And then the only bug that you can see is the first one, right? And then maybe yeah, you can get the length of the stack using this length function. But yeah, still you append, and then when you call pop, then the last element that is put it in will be popped out. So as you can see, 1, 2, 3 is appended in, but when you call pop, then 3 will be popped out, right? And then 2, and then 1. Right, and then that is the use case of stack. And yeah, let me just get right into this this stack usage example. So every time we talk about stack, there is a classical um, question. It can come in exams or practices everywhere, right? And then the the question is, if you have a bunch of brackets, what will you do to check if it is matched pairs, right? So what what I mean is, for example, this is a I don't know, I would say um, a whole bunch of brackets, right? You have this round bracket, you have this square bracket, you have this large bracket, and curly bracket, right? And then if you have like a large amount of those kind of brackets, then how do you check if it is matched? And you know for now, it seems readable, and then you can still tell it by your eyes, and then just check. But with using stack, there is a smarter way to check if those bunch of brackets are matched. Okay, I'll give you like 2 or 3 minutes to think about it. Why it is useful to use stack, and then how would you implement it using stack. Okay, yeah, I mean, think about it and try to have some basic ideas of how would you do it. Okay, so yeah, after a little bit of thinking, I should reveal the answer. So this program is a classical one to figure out if those pairs are matched. Okay, and then yeah, I mean, as you have noticed here, it says if underscore underscore name is equal to this underscore underscore main. And this is just the main function in Python. Um, Even though it looks weird, but it is the main function, and it is sort of like the public static void main in Java or anything. But I mean, feel free to like not write anything, because if you can, if you just delete this code and then unindent, um, it still works, right? It still works. Okay, so um, yeah, it still works. So let's say you have a whole bunch of brackets like this, right? And then we're going to this function called r brackets balanced, right? And then the first thing we do is we just create a list called stack, and then for each character in that expression, if character in this, so if character is the left half of the round bracket, left half of the curly bracket, left half of the square bracket, then I will push that into a stack, right? Um, why do we do that, right? Because when you push that into a stack, then you're sort of storing, the layer, the layers or the architecture of that. And then if that is a right half of those three brackets, right? Else, this case, and if it is not if it is not in stack, so return false, right? Because if it is not in stack, then it will not the bracket will not be matched, right? And oh, sorry about that. If not stack means the stack is empty. Okay, sorry about that. If not stack means stack is empty. It is basically saying that if you have a right hand right side of the bracket, but you do not have any kind of left side of the bracket to be matched, right? If not stack, if every time you try to not a I would say a list, it means that there is nothing in it. Okay, so if there is nothing in it, then you return false. Okay, and then if there is something, then you actually pop it out, right? And then after you pop it out, then you will need to check if the current character is the left hand side, right? After you pop it out, if it is the left hand side, then you know and if the character that you append in is the right hand side, is not the right hand side, then it will be false, right? So the stacks are not matched. Okay, and then you return false. And then if the current character is this curly bracket or this square bracket, it works the same. Okay, so yeah, and then if stack, so after each iteration, this is so far what we did is after this iteration, then we are basically done with the string, right? And then you don't know whether there is still elements or still left brackets left in the stack. If there is, then it is still not matched, right? It is not balanced. So you would return false again. And if there is nothing left, then you will just return true. Okay, so that is actually balanced. Okay, so if you are not very clear, then um, I will, what I will do is I do print stack, right? And then, yeah. So initially the stack is empty, and look at this. This is a, oops. This is a perfectly balanced expression, right? So you have a large bracket, you have a small bracket, and then you have a large bracket, and then a large bracket in immediately closes that large bracket, and then you have a small bracket that is matched to this, and then you have more left side of the bracket, and as you can see, this part is perfectly balanced. This part is oops. This part is perfectly balanced, and this bracket is perfectly balanced, right? So the input is, if you use our eyes to check if it is balanced, then it is indeed balanced. And what will happen when we do the algorithm? So we have one of the left side, so we append in one of the left side, append in, and then we have a large bracket again, right? So we append in. So right now we have a right hand side of the bracket. And then if we scroll up to here, then, well, the condition is, well, else, then because it is, this character is not in, um, not in, is not the left hand side of the brackets. So we get into the else case, right? If not stack, means stack is empty, but apparently stack is there has something in it. So we'll not get into this case. And then you pop out, right? The current character is the left-hand side of this curly bracket, right? And then you just check. Oh, here, current character is the left-hand side of the curly bracket, and the character is indeed the right-hand side of the curly bracket as well. Then after this, you do nothing, right? And then this element is already popped, right? So this left-hand side of the bracket will pop out and become something like this, right? And then so on and so forth. You have another right-hand side of the round bracket, and then you have this. This is matched, so you pop out. And then now you have more left side, right? If you have more left side, then append in. And then you have more right side, then pop out again and again, right? And then left side and right side and popped out. And then finally you have a right side of the curly bracket, and then it actually breaks, actually pops out this the first left hand side uh, bracket, curly bracket. Okay, so that is the way to tell that this one is balanced. Okay, and then what if it is not balanced? I'll show you what happened. So you can do something like this, right? Then you will do blah blah, and then you can do blah, whatever you want, right? Literally whatever you want. Right? If you run this, you can see it is not balanced, right? And then those ones keeps the same. And then if you have those left hand side brackets, right? And then this one is immediately not matched, right? You have a round bracket, and then you have a closed bracket that is not round, it is a square bracket. So this one does not work. Okay, and then you might also have those cases like something like this, right? And then you have a blah 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 blah, right? And then after the last left hand side of this is paired, right? But there is two more right hand side brackets, and then it actually get into here. So check empty stack after after all the character. Oh, it is actually the case here. If not stack, return false, right? If the stack is still not empty, then return false. Okay, and then you have a bunch of stacks. There is this too much right hand side of the bracket. There's also this case, right? And then after you just push in, a bunch, right? And then you don't have the pop, so the stack is not empty when it's exiting, so it returns false. Okay, so that is basically how you check this bunch of brackets, if they work or not. You can go ahead and play around with it. Try different inputs, right? You can sort of just manipulate this expr expression string, and then give in a bunch of them, and then test your code thoroughly. Yeah, even though it is already proved that this code is working. But yeah, I'll give you like 5 to 10 minutes to see, um, and to try to understand what is going on in a code, and ideally, you can actually rewrite this without looking at the code. Okay, so yeah, if you can rewrite this those code that we have talked about without looking at them, you're basically good, right? But if you cannot, then try to figure out what is going wrong, and then what is the detail that you did not pay attention to, right? So that will be very helpful for you to be better at programming. Okay. All right. So I will give you guys a 5 minute to 10 minute time slot for you guys to actually take in yourself. All right. right. Hope that you guys start to get more familiar with this program. Yeah, and I hope that this kind of thinking, at least, will be useful to your future programming career. All right. Yeah. So after this, we will talk about a very important idea, and it is one of those basic searching algorithm. We're not done with sorting yet, but I am just want to give you guys a little bit more exposure to different sorting sorting ideas. But this binary search thing is a pretty, I would say it's a pretty basic idea, and it is a good introduction to this idea of divide and conquer, right? You know, um, recursion is another way of divide and conquer, but binary search does not use recursion, but it is the idea is very, very similar. Okay, so what is binary search? Binary search is that assume that you have to find an element in a sorted array, right? This scenario is saying that if the element is already sorted and you try to find an element into it, or I don't know if you have heard of this joke, but I feel like I just want to say it to you guys. So 是这样的，之前听说过一个笑话，就是说一个图书管理员阿姨，然后呢有一个同学带着一堆书跑出去了，对吧？然后那个图书馆的时候，不是会有，比如说，如果这个书没有扫过，然后它那个门就会叫，对吧？就不让你出去嘛。意思就是，比如说你没有扫过，然后你可能得扫一下才能出去。然后呢，那个小同学好了，就开始把那一堆书放到桌上，一堆一本一本扫，好吧，开始一本一本扫。然后图书管理员看了纳闷了，你这扫的也太慢了。那要不这样，我们把这一堆书分成一半，分成两半，好吧？一半扫一下，看看有没有那个的书没有扫过的，就是没有登记过的书，好吧？另一半再扫一下。如果说只有一本书没有扫过的话，那么情况会是什么呢？情况会是，比如说你扫其中的一半它没有任何的反应，对吧？就是它那个门嘛，就是你把这一堆书前后大概感应一下，让这个门感应一下，然后那个门不会叫，对吧？然后另外一本书另外一堆书扫一下，肯定会叫嘛，对不对？因为有一本书，有一本没有扫过的书进出了一下门。OK，那么，那么这个阿姨这个图书管理员阿姨呢，就继续分，好吧，继续分，一直分到有最后一本书就是把它分出来了，就是这一叠书一直除以二，一直除以二，那么这一叠书的就是没有那个的，就是有一堆没有扫过的书的那个大小会越来越小，越来越小。然后呢，最后就会找到一本，对吧？然后这个就是 binary search 的 idea，就是说 you divide and conquer, right? You divide it into two halves and check if one half has the element that you want, right? If that half does not have it, then check the other half, because if that is not in that half, that will be definitely in the other half, right? And then you don't have to break it into two, right? If you want the algorithm more sufficient, you can break it into 3 parts, 5 parts, 10 parts, and as many parts as you want, right? But like in this case, the idea is just break it into 2 parts, right? And yeah, so if you cut if the condition is for an array and it is sorted array, then you can just compare, right? um, if a specific number, let me scroll down, 2 3 4 10 40, right? And then if you want to check if find what a number that you want, right? You don't just go ahead and do if 2 is the number that you want. No. If 3 is the number that you want. No. Like this is too inefficient, right? And since this is a sorted array, there will be some characteristics that you can use. For example, 4 is definitely less larger than 2, right? The array on the right, well, the element on the right, sorry, not array on the right, the element on the right will definitely be larger than the element on the left, right? So if you break that array into half, then you want to check, for example, if 10 is in one half or in the other half, right? You only have to compare where you cut this array. For example, you cut at between 10 and 4, right? You know, and then yeah, to just make this case complicated, I'll add a 7 into it. Okay, so suppose you cut between 4 and 7, right? And then break that into 2 arrays. You will check 4. Is 10 less than 4? No. So this half of the array does not have what we want. So we can ignore this, right? Is 10 larger than 7? Yes. So definitely it is somewhere in this array, right? And then we are again break it into half, right? No matter which half you break, um, right? And then you just check it again and then check it again. Okay, so that is the idea of binary search. Okay, and I will just show you guys a video of that to guys understand easily this idea.
There are many different ways to put a shelf of books in order, alphabetically, by author or by title, by subject or by the colour of the spine. Those are all valid approaches for different situations. If you're running a bookstore that has a lot of customers coming in and saying, oh, I don't remember the title, but I know it was red, then sorting by colour is a reasonable approach. In 1876, an American librarian called Melville Dewey published a 4-page pamphlet describing how he thought a public library should be ordered. Before Dewey, books in many libraries were ordered by when they were purchased. As new books arrived, they would just be allotted to a shelf or to a box that matched their size, and there'd be a central card file somewhere listing where everything was. You would have to ask a librarian if you wanted a certain book, and they'd retrieve it for you. Just browsing the shelves wasn't a thing. Dewey gave each subject an index number and then said that the shelves should be ordered by that number. Over the years, the Dewey Decimal System became a standard. Dewey had solved a serious problem, how to sort and find information without having to bother the head librarian. And because books were clustered by their subject, it encouraged general interest browsing of the shelves. Side note, While researching this, I found out that Dewey was a terrible person. Not in an, oh, but he was of his time way. He resigned from the American Library Association because of sexual harassment complaints in 1905. How bad do you have to be in 1905 to get kicked out? His sexist and racist biases made it into the early versions of the Dewey Decimal System. Lots of libraries these days use completely different classifications, but yeah, we do still remember his name. Anyway, here's the key point. By creating a useful index and sorting by it, readers could find books more quickly. That same principle of indexing applies to computers and has since the early days. There are two basic ways that a computer can search: linear and binary. Let's say you've got a stack of cards. They've got numbers on them that are somewhere between 1 and 50, and you want to find lucky number 30. If it's a shuffled stack, then there is no shortcut. You just run through looking at one card after another, after another, after another, until eventually you find number 30. That is linear search, going through every card in a stack, every element in a list, until you find the one or many that you're looking for. That'll work on any list in any order, but most of the time it will be slow. But what if the cards are in order by number? Sure, you have to spend some time to sort them. I've got a whole other video about that. But once you've done that, once they're in order, you can use a binary search. Binary not in the terms of like zeros and ones on disk, but binary in terms of splitting things in two. You look at the middle item of the list. Is it higher or lower than the number we're looking for, 13? So in this case, it's lower, so we can forget about the first half of the list, and we can do the same again. Look in the middle of what's left, forget about the side that we don't want. Look in the middle, forget about the side we don't want, and so on, and so on, and so on, until eventually we find the card we're looking for, or we know that it's not on the list at all. Okay, with 11 cards, binary search doesn't make much difference, but with 1 million cards, it is lightning fast compared to linear search, provided that the list is in order. But a stack of cards is a simple example. A database is much more complex. Let's say we don't just have numbers on the cards, we also have letters, and let's add some colors as well. We can't sort the cards by more than one of those properties at a time. So right now, I can use binary search for number, but not for letter or color. In the same way that librarians can sort their books by title or author or color, you can only optimize for one property at a time. For everything else, you've got to run through every book on the shelf, every card in the stack, every item in the list, unless you use indexes. Now, physically rearranging data on a hard disk, moving the cards around, that's called a clustered index. It's like making sure your dictionary is in alphabetical order, because that's mostly how you're going to use it. But a non-clustered index is like the index at the back of a book or a library catalog. It's a separate store of just the property you're interested in, stored in a simple, easy-to-access format. If I want to find the card with the letter K on it, well, I can do a binary search through the index at speed, identify the number of the card, and then use another binary search to go straight to it. If I want to pull all the green cards, well, I can pull just those out of the color index, note down all those numbers, and then pull just those cards. There's no linear search happening anywhere. Again, it doesn't make much difference with 11 cards, but with 1,000 or 1,000,000 or 1,000,000,000, that's the difference between waiting hours for a response to your query and having it in a fraction of a second. Of course, each index that you add takes time to create and space to store. If your computer has ever been slow because of the indexing service on Windows or Spotlight search on Mac, that's it, taking the time to run through all your files and index all the properties that it can, so that when you type something into your search bar, it'll be able to reply as quickly as possible. But every time you make any change to your database, if you add, remove, or change something, you also have to keep the indexes, whichever, up to date. So there's a skill in choosing which properties, which fields in a database you want to create indices for. If you're only going to search by color once or twice a year, it might not be worth indexing. As with many things in computer science, there is a trade-off between space and time. Now, Google say that their full search index is 100 petabytes in size, and they're customizing every result from it for every user, usually in under a second. Even after all the changes to Google over the years, even after all the space that they've given over to knowledge boxes and adverts, even after all the optimization that they've added to give the user exactly what they want, Google still put the time that it took to answer every query on every desktop search result because they're still proud of it. Because the logistics and computer science skills required to do that are the sort of thing that PhDs are written about. Or because it's a trade secret, they're the sort of thing that commands very, very high salaries. It's a long, long way between Dewey and his decimal system and the Google search result, but the basic principle, create an index, is the same.
Okay, yeah. So that was the video to introduce you about binary search, and yeah, just give you a little bit of history class of sorting and searching. Okay, and yeah, so let's get right into the source code. If that is something that is worthwhile to do. And we just always start with the driver code, which is here. So we have an array, and then we have a target that we want to find, right? And then we have a function called, and then the result is equal to binary search ARR and X, right? And then this function, this binary search, if the element is not there, so it will return -1. Other than that, it will just return the index of X. Okay. And let us get right into the function itself. So it is not hard. It is just a few lines of code. And what it says is, okay, so for, you have a low and a high, right? You have a low and a high. And at the first time that you call this function, then the low will just be 0, right? The high will just be the end of an array, right? So a length of array -1, right? So a length of array -1 just means that the last index of the array, right? And then we just initialize mid equals to 0. Okay, and then this while condition just means while low is less or equal to high, right? Okay, so as long as this index, the number for low is on the left side, then the number for high, then what we will do is we go ahead and do mid. So mid is just the middle point that we are looking at, right? So you just do high plus low, and then integer division by 2. Okay, so that is just to find uh, the middle index of that entire array. Okay, and then the integer division just makes it always an integer instead of, like, because Python, if you do divide right away, then what if high plus low is an odd number, right? And then if you divide it by 2, you will have a decimal, right? And then that is not what we want. We just use the integer division, right? And then if x is greater than the mid, so I would say you just select that mid as a pivot. I mean, pivot is just a point. Okay, it is just a point of interest. If it is larger, if x is larger than this middle element, then you just do low is equal to mid plus 1, right? So you're basically ignoring this half of the array, right? And then you're basically you're basically doing that. This is now mid, right? And if you don't see this, I will just add a bunch of printing message. Change low into print change high into right, and then I just print of mid is mid. Okay, so yeah, just let me write some more. Let me write some more printf statement just to demonstrate you how this binary search works. Okay, so yeah. Let me add this as well. Array mid. Okay, so first we are using 4 as the middle point, right? Why that is the middle point? Because think about it. Low is equal to 0, and then high is equal to 0, 1, 2, 3, 4, 5, right? This number 40 is 5, right? 5 divided by 2, integer division gives you number 2, right? So mid is 2. And then which that correspond to is this number 4 here. So we treat that as the middle point, right? And then we check if the number 10 is larger than 4 or less than 4, right? So if it is larger than 4, then the low is equal to mid plus 1, which means that this is mid, right? So low will then be the index of this one, which is 7, right? Change low into 3, and that is 7, right? And then we're basically ignoring the left half of the array, right? And then when you do that again, right? So 0, 1, 2, 3. So this is 3, this is 5, 3 plus 5 is 8, divided by 2 will be 4, right? Divided by 2, yeah, divided by 2 will be 4, right? The mid is 4, which is 10, right? And then else return mid, right? So this is the case where you just do the division, and then you found out where exactly this element is, and then you just return the index. Okay, and then this is the case is pretty nice. Okay, and then what if we try to find a element that is not in the list? Okay, so and then I will just print here, print low high, then high. Okay, and then those printing statements are just to help you to understand better the binary search. Okay, so what you're trying to do first. So this is the step. This step is the same. So you go to 4, right? Mid is 2. You go to 4, and then you just ignore the left half and do the right half, right? And then you find this index is 10, right? And then you just change low into 5, which is 40. Okay. And then what happened is that the mid is 5, right? And then it is 40, and then you check you check 40 again, and you find out that 12 is less than 40, so you are basically moving high to mid minus 1, right? If you do high is equal to mid minus 1, and then mid and low and high are just 5, then high will just be equal to 4, but low will still be equal to 5. And then this while loop is failed. Okay, this while loop is failed. High is less than low, right? And when high is less than low, then you just return -1, which means that the element is not present in the array. Okay. Yeah, so that is the entire algorithm. Sometimes it is tricky to play with those indexes, but it is very necessary for you guys to get good at it. That is it for this binary search algorithm. And I hope you also spend, I would say, 5 to 10 minutes to think about this algorithm. Maybe give more inputs and try more values to search for. Right? Just to inspire you, you can do this. Right? You can do when x is equal to 2. Right? And then you just right, and then because this is the leftmost index, this is the left and rightmost elements to search for. So that will be interesting to take a look at and to see if those bound cases work for you or for your algorithm, right? And then yeah, I mean, even though you can find all of those kind of resources online, but it is still a good habit, and then I would say a good practice to your logic or your ability to write algorithm. Um, if you just try to replicate it, right? I mean, replicate it just means like without looking at the code that I give you, try to implement binary search. Okay, so yeah, I will give you guys like 5 minutes to try to understand this algorithm and try to play with it. Okay. Okay, so yeah, I hope you guys get more familiar with this binary search already. And let's actually start today's notebook. Um, First, there will be two kind of sorting algorithms that I want to mention. There will be more, but this idea merge sort and quick sort are just it is more advanced than selection sort and insertion sort, but it is not too complicated to handle. But I would admit it is very challenging. And yeah, in terms of in terms of sorting, then I will first let you guys watch a video. Then I will talk about how it works. Okay, so it is our favorite dance video again. Um, yeah, I just feel like it is a good way to visualize those stuff. Okay. Yeah, definitely interesting video. There are, it is just that when I was in grade 12, or it is since it is called a grade 12 ICS course, then my programming teacher always give us to watch this before we actually start to talk about sorting. So yeah, I figure that that is an interesting video, and that is just a good way to visualize how sorting is being done. Okay, so yeah, the idea is called merge sort, and oh, for sure. Let me copy this link. Okay, so like quicksort, since we haven't talked about quicksort, we'll just ignore that. But yeah, we will talk about quicksort right away, right after the merge sort. And the merge sort is a divide and conquer algorithm, as you can see. And the way the reason I introduce merge sort now is because we just finished binary search, right? And it has very similar ideas in it. Okay, and because both of two are divide and conquer algorithm. Okay, it divides the input array into two halves and call itself for two halves, and then merge the two sorted halves. Okay, you might be pretty confused of what I'm talking about, but yeah, let me continue so that you can understand me better. The merge function is used for merging two halves. Okay, and the merge array LMR is a key process that assumes that the array L to M and then the array M plus 1 to R are sorted and merges the two sorted subarray into one. Okay, and then yeah, C implementation, ignore that. We have a Python implementation. So this is a pseudocode. Okay, so merge sort has an array and then a left and a right. Okay, and then if right is larger than the left, so that is basically the same idea as as the binary search, which has high as larger than low. In this case, it is right as larger than left because we're dealing with indexes. Okay, and then find the middle point to divide the array into two halves. So you're gonna again have a middle M is equal to left plus R minus left divided by 2. Okay, so I mean that is basically saying that R plus right plus left divided by 2, but it is the same thing, right? So just to find the middle index. And then call merge sort for the first half, and then call merge sort for the second half, and then merge this left, middle, right. Okay, that is not easy to understand. It is recursion and divide and conquer at the same time. It is pretty challenging idea, but if you look at the program itself, it can be simple. Um, it can be pretty simple, even though it is quite a few lines of code, but I would guarantee you it is very simple. Okay, so the following diagram from Wikipedia shows the complete merge sort process for an example array. So if you have this array, And then if we take a closer look at diagram, we can see the array is recursively divided into 2 halves until the size becomes 1. Once the size becomes 1, then the merge process come into action and start merging array back until the complete array is merged. Okay, so assuming that you have a array like this, right? So 38, 27, 4, 3, 9, 8, 82, and 10, and blah, 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 right? You divide that into 2, okay? You divide that into 2, and then you divide that into 2 again. You divide, you divide, you divide. And then all until you divide everything into a one single element. Okay, then we try to merge it. By merging it, I mean if the left-hand side is larger than the right-hand side, then you choose the left-hand side for the first, and then you choose the right-hand side for the next. And then as you can see, we are taking one element, and every time you're comparing against it. And then, yeah, it is not easy to see for one element, but for one element is just comparing against itself, right? And then if one side does not have any elements in it, then you just move everything there. Okay, so it will come more clear when we talk about this case. So first we have 27 and 38, right? So 27 is less than 38. So we will move the 27 into the next array, right? And then right now we does not have anything on this side, right? So we just move 38 into the next slot because, if there is only one element, it is already sorted. It is just this idea. And then you have the same thing. You have 43 and 3, right? And then you just try to sort it. And then, um, you know, ideally, we should come into here, right? Yeah. So let's talk about this first. Now we have 2 elements on each side, right? This side and this side. And then we have this. So we have 3 and 43. Oh, by the way, this number, the screen number here, are just a way to tell you what are the steps are the recursive calls, right? Because if you call it recursively, then it will go deep and deep and deep until it cannot go any deep, right? And then it will go back and it will traverse back. Okay, and then you'll have this at the first stage, and then you will have this second, and then you just divide it into it and then call it. You divide it into it and call it, right? Because it is a sort of a recursion idea. And then if length is larger than 1, you calculate this middle, calculate this left, and you calculate this right, and then you just call merge sort again, right? So it is keep dividing and dividing and dividing until it cannot be divided anymore. Okay, so 1, 2, 3, 4, and 5. That is when this 4 cannot divide itself anymore, so it tries to call merge sort right, right? But merge sort right is just this, so it cannot divide anymore. And then you have this this sorting, right? You have this merge, right? So that's merge. Okay, so yeah, that is the merge. Yeah, so you're basically merging those 2 elements as the first 2 elements. So 27, 27, 38. And then you cannot do anything. You cannot do anything there. And then after you're done, then how I supposed to say it? Um, on the previous level, this merge sort left is completed. Now we are going into this merge sort right call, right? And then you have this half, but you will have to call merge sort right, and then you just call it again, and then call it again, right? And then you again divide it into two separate halves, and then you go ahead and merge it. Okay, and then we will talk about merge later in detail. Okay, and then as long as you come into this stage, then you can be able to merge to this large list, which is a 4-element list. And how does merge works? I'll show you the code. No, I'll first explain you the idea, then I'll show you the code. Okay, so it is basically taking each one element from the list, because those two lists are already sorted, right? So those two lists are already sorted, and as long as we figure out how to merge those two sorted lists, then we will have a larger sorted list, right? Is that idea correct? Right. So that kind of idea is called divide and conquer, which means that as long as you have something that is done, right, and you have another something that is done, and then you break it into small parts. As long as those small parts are done, and then those good small parts can be merged into a larger parts that is maintained the structure, which is the state done, and in this case it is remain sorted, right? So as long as those two subparts are sorted, we have a technique that can merge those two lists and make into a larger sorted list. And that technique is called merge. And this idea of merge is that we take an element from each list. We should take the first element from each list. And what will happen is that we are comparing those two elements. If one element is smaller than the other, then we put that into the first element, and then we move our index to the other number. So the first will be, I will just draw it out here. So what will happen is I will point to this as my first element, right? I will point to this as my first element, and I'm comparing 3 and 27, right? And 3 and 27, since 3 is smaller, 3 can be moved here, right? And then I will erase this pointer because 3 is already moved here. Then on the right side of the list, I'm pointing to here, right? This 43. And then I am comparing 43 and 27, right? Because as long as it does not move into the next stage, then this pointer thing does not change. Okay, so we have 27 and 43. Right now, 27 is the smaller one. So I move this 27 here. And then I erase it. I move the next one here, right? 38, right? And then we do the comparison again. So you would do 38 and compare to 43. And then 38 is moved here, right? And then you erase this. And then as long as one of the array does not have any elements anymore, then we will just move all of the other list into this into this larger sorted list. Into this larger sorted list. Okay, and then as long as we are done with this, we're done with stage 11. Oops. Yeah, I just paused the sharing the screen. Sorry about that. I hope that you can still see my screen. Okay, so as long as we are done with this half, so another upper level of merge sort left is done. Okay, so the merge sort left by called by the original array is done, right? And then we are go ahead and call merge sort right. Okay, and then we continue with the right half, right hand side of the array, and then you're basically doing the same thing, and then blah blah blah, you're doing the same thing, and then you merge to here, and then the last step, just I think I have already told you guys this, but I will just repeat myself again. So how we merge this to array, right? The way we merge this to array is just so you have a pointer again, right? This is moved to here. I'll make faster, and then we're pointing to here, right? 9 is less than 27. I'll move this, and then I'll point here, and then I'll erase this. And then 10 is still less than 27. Then 10 is moved here, and then I will point to this 82, right? And then 27 and 82, 27 is definitely less. I move here, and then erase the index, and then 38 is less than 82, move it here, erase, point to 43 is less than 82, move it here, erase, and since the left hand side array is empty, then dump all right hand side to the index, to the larger array. Then we are basically done. Okay, so that is everything for merge sort. I hope you now understand the idea of merge sort. Okay, I hope that you understand the idea. And let's actually get into the code. Okay, so as always, we have this. We have this driver code, which assigns a variable, and then yeah, you just do print list, which is just another dumb, which is just a print function. It does not actually do anything. You can just do print arr, but it doesn't matter. Okay, so it prints the list, and then you call merge sort, and then you print the list again. Okay, so you don't have to worry about this driver code. Driver code is easy enough. The only thing we need to take a look at is merge sort. Okay, so merge sort. In Python, merge sort can be done in fairly simple way. You can have this as long as if length of the array, so the length of the parameter is larger than 1. As long as it is larger than 1, then we are finding the middle index of the array, right? And then we are dividing the array into 2 halves using the array indexing, right? This is so much easier than other language, so you should be appreciated, because you will need to copy it manually in other language using a for loop, but in Python this is so much easier. Okay, and then sort the first half. So you just call, so left is equal to array column mid, right? That column mid just means that from the start into mid, right? Start from the start to mid, and then you just call merge sort on that left, right? You first sort the first half, and then you sort the second half, and then you try to merge it. Okay, so those code here, so those highlighted code basically are composed of 3 while loops, and those 3 while loops are just the logic for merge. Okay, and then those above are recursive call. So recursive call means it's just calling itself again with other parameters. Okay, and then after since we're done with this recursion, and then what we'll do is we will do the merge, right? So we are having 3 index. I equals to j equals to k is equal to 0, right? And each of those are index for the left array, the right array, and then the ARR. Okay, so what will happen is while I is less than the length of L, and J is less than the length of R. So that means, you know, for example, if you have 4 elements in the left, and then you have 3 elements in the right, this for loop will only loop 3 times. Understand? Because what will happen is, because those 2 conditions need to be correct, as always, not as always, but these two needs to be fit at the same time, right? Because this is an end, so both needs to be true, right? So that the while loop can be continued. But so this I and j will, if left has a length 4 and then right has a length 3, the I and j will both equals to 3, and then this loop will be broken out. Okay, so basically it says that it is meaning that um, as long as those 2 lists have the same length, that you're basically do all the merging. And then I'll just show you without going into this loop, this loop here. I will first show you this. So if there's any element left in the left side of the array, then we just basically dumping. By dumping, I mean throw everything to the sorted list. Okay, to the larger array. So ARR just is the larger array that we talked about here. Okay, so we basically, if the left is not done yet, but the other one is already empty, then you just dump it, right? While the right hand side is empty, the right hand side still has elements in it, then dump everything on the right. And yeah, just to note that either only one of this will happen, right? Like only one of this while loop will happen, because on here, you will have to sort of done iterating through one list, right? You're basically saying that when one of the list is empty, then this will break, right? And then you sort of do not know which one is empty. So you will write while code for while loop for both of those elements, because you don't actually know when and then which list here will be empty first. Okay, so you'll have to write. But this code has the beauty of um, even though you don't know which one will be empty first, it will only execute one of the for loop, one of the while loop, and it is because this one, right? It is because this while loop, and this while loop just means that when I is less than length of L, and then j is less of R, right? So it is just iterating that shared index, right? In the previous example that I gave you, it is just iterating through 0 to 3, right? And then you're basically just comparing which side is larger and which side is less. If left side is less, then we make the larger, so we assign this larger array with the left-hand side array. And then don't forget to add increment the index, okay? And then otherwise, you do the right-hand side and then increment the index again. And then after this if else, then one element will be put in the larger array anyway. So we will always need to uh, increment by one, right? So this is the while loop, okay? And I don't think I have time to go through quicksort, but today. But I will just explain merge sort better, and I will try my best to explain it in like next 12 minutes. And yeah, if you don't see this, I will give you some print statement. Merge sort out. Okay. Calls merge sort on list. Like if you are not familiar or you don't know what is happening with this code, then I can have a print statement here, right? And then I can print, mid is, and then I do mid. Okay, I do mid, and then this well does not. Okay, yeah, I will just print out as well. So print left is L. Right is R. And then those are recursive calls, so you don't have to print anything. Then what you will need to do is again I will print append li into ARR, right? And then I will print append RI into ARR, right? And then I will, yeah, that is, it is in the while loop. I don't want to print too much, so I will not print here. But after this, I will print ARR merge done. Okay, I will just say merged ARR, and then I'll do this, and then ARR. After I run this, magic will happen. Yeah, just kidding. Okay, so yeah, this is the driver code. I don't like the driver code, so I will delete it. So that's a lot of print statements, but it doesn't matter. Calls, merge, sort, on list, blah, right? So this is the list that we're given. Mid is 3. So what happens is you have mid, right? You calculate the mid, right? A mid is 3. So what happened is the left is from 12, 11 to 13, and then right is 5, 6, 7. And then what happened is I call merge sort on 12, 11, and 13. Okay. And then I get mid again. Okay. And then I break it into left. Left is 12, right is 11 and 13. Call merge sort on 12. So 12 has only one element, right? So if 12 has only one element, then it is already sorted, because here has a condition if length of array is larger or equal to 1, larger than 1, right? If if it is larger than 1, then we can try to we can try to split it and sort. But if it is equal to 1, then you don't have to do anything. Okay, so because when it's larger than 1, you just wait for merge. Okay, now we call merge sort on list 11 and 13, right? And then you get mid again, right? You get mid, and then the left is 11, the right is 13. Call merge sort on 11. Okay, nothing to sort. Call merge sort on list. Then the merge sort on list 13, then it does not have anything. And then append 11 to ARR. And then yeah, I will do this. I will actually try to print it. So left not empty, append, and then you do li. Okay, so that is the clearest program ever for merge sort. Okay, you are printing out everything, and then that is the way you can explain this. Oh shit, okay, yeah, I forgot to change the index. It's J. Okay, so where was I? So here, calls merge sort on 11, calls merge sort on 13, and then we are trying to merge, right? So we append 11 into ARR, and then we append it. Then the left side is empty, the right side is not empty. So R not empty, append 13, right? And then the merged array is 11 and 13. Okay, and then append 11 into ARR, append 12 into ARR, and then R dot empty, blah, 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 and then I try to merge ARR. Okay, so yeah, make things more clear, even though I think it is a little bit extra, but I will do this. Merge, merging two arrays out, put a space, R. Two arrays L and R. Okay, so that is the merge call. That is the merge call. Let me see if there is. Yeah, I will just add a printf here. Print empty line. Okay, so that is very, very clear. So yeah, here you're calling merging two arrays with the left is 11, right is 13, and then you have merged, right? And then that is used as your right? And then you're merging this two array. Left is equal to 12, and then right is equal to 11 and 13, and then you try to append 11 into array, you append 12 into array. R is not empty, then because the right side has one more element than the left, then the merged array will be this, right? And then you again cause the merge sort on this, and then blah blah blah. Okay, so that is the program flow. If you have the patient, you can go through everything on this when you're free. Then yeah, I have this analysis for the time complexity, but I don't think this is something that is required to handle for a grade 12 student, grade 12 student, because yeah, this course is credit for grade 12. If you are interested, you are welcome to read and welcome to ask me about it. I will not introduce too much about this. I will just like spend 2 minutes to introduce it really, really briefly. Okay, so to analyze this time complexity, this T of n, this T of n is the original function call, which is this function call, right? And then this T of n, what will happen is that you will have a recursive step, right? You will have two recursive steps, and then each of them have complexity 2 times T of n, and then T of n divided by 2. What happened is this 2 represents the two merge calls, two recursive calls. Sorry about that. Because we have like this merge sort on the left and merge sort on the right, right? So we have two recursive calls. And how much does each recursive call cost? It is basically doing Tn divided by 2, right? And Tn divided by 2 is the size of the input, right? And you guys are having like divided by 2 every time and divided by 2 every time. And then this zeta n, what does this zeta n means for? This zeta n means the cost for merge, right? And then basically every time you do merge, you will have a upper bound of time complexity n, right? Because you are going through the array every single time, right? And then even though sometimes are small arrays, but you cannot guarantee how small they are. And the upper bound of it will just be the last one, right? That dominant one, because you will have to merge the entire thing, because the last merge step will have a loop of n, right? So that merge cost will have theta n. And then if you are interested in recursion tree, you will take a look. You can go online and take a search, okay? And then, but idea is that this recursive step will take log n time, and because of the binary search, right? Binary search. Oh, I forgot to mention, binary search takes log n time because it is, you only have to search 2 to the power of something times, right? Because if you have 100 elements, and then if you do binary search on 100 element, then you only have to do like 4 or no, 6 or 7 times, because 2 to the power of 6 is 64, 2 to the power of 7 is 128, right? And then you at most need to search for 6 or 7 times, then it can be done, right? And this is the same. So this recursive step is log n, and then you have each step. For each log n, you have a theta of n, which is for each log n, you have a merge step which costs theta of n. So you can actually multiply them, because it's for each, right? For each just means that you have to do that every single time for log n time merge, right? So it just multiply them and you will get n log n. And this is the first n log n algorithm for sorting that we studied. Okay, yeah, again, as if you so there's a thing called recurrence tree method and master method. Those two methods are very useful when you're trying to analyze what are the costs for this algorithm. If you're interested, go ahead and take a look. If you're not, it is not required. But if you have data structure and algorithm course, and it will be definitely teached. At time you might feel it challenging if you don't take a look at it right now, right? If you since we have this chance, right? When I was in grade 12, I don't have this chance. I learned this in university, and so yeah. So I feel like if you guys, I know this topic is hard. Understanding recursion is hard already. Understanding merge sort, but like think about it. This entire algorithm has 2 merge calls, 2 recursive calls, and a merge step. So it is not that complicated. If you just look at it and then try to like debug it and see what happens using those printing statements, like it will not be as complicated and as scary as it is. Okay, wait. There is something weird. Appending array 5 into this. Yeah, append. Oh yeah. Once again, I forgot to change the index, so this should be changed. But yeah, I mean, this is now correct. 5, 7, 6, 7. Okay, so yeah, again, if you debug it through, you will find it so much easier to read this code. Well, those code are well commented, and then every step it is already printed out. So I hope that it is a good learning resource. And once again, if you're interested in this time analysis, then let me know. I will send more material if you guys are interested. This will be helpful if you go into university, go into data structure and algorithm course. It is a very, very important course. If you want to do lead code and ace any kind of interviews, you will definitely need those, and those are just basics. So yeah, anyways, I talked too much today. We will leave this quick sort to Monday, and then we are just gonna introduce the topics in computer science, which is like sort of a research unit for you guys to actually dig up the stuff that you're interested in. Other than that, we will get into the design project that we are talking about next week. Okay, so that is all for today's lecture. Is there any kind of questions, or is there any kind of comments? Are there anything to ask? Sounds good. Okay. All right. That's it for the end of the lecture. Everyone, stay safe and have a happy weekend. All right. See you guys. Are you guys asleep or something? Thank you. Yeah. Thank you. Bye. Yeah. After I say goodbye, nobody actually leaves. So I am assuming you guys are asleep. All right. Seriously, I'm gonna end this call. All right. See you guys.